Stress. Define the term stress. Give its units and dimensions. Describe the different types of stress. Stress. If a body gets deformed under the action of an external force, then each section of the body, an internal force of reaction is set up, which tends to restore the body into its original state. The internal restoring force set up per unit area of cross section of the deformed body is called stress. As the restoring force is equal and opposite to the external deforming force, therefore stress is equals to applied force upon area. It means if area is increased, then stress is decreased, and applied force, as much as the applied force, stress also increases accordingly. So applied force upon area. If we have to calculate stress, then we have to divide amount of force divided by amount of force applied divided by area. SI unit of stress is Newton per meter square, Nm minus 2, and the CGS unit, centimeter gram second unit, is Dyn per centimeter square, Dyn centimeter minus 2. The dimensional formula of stress is ml minus 1 t to the power minus 2. Types of stress. Tensile stress. It is the restoring force set up per unit cross-sectional area of a body when the length of the body increases in the direction of the deforming force. It is also known as longitudinal stress. Next, compressional stress. It is the restoring force set up per unit cross-sectional area of a body when its length decreases under a deforming force, that is compressional stress. Next is hydrostatic stress. If a body is subjected to a uniform force from all sides, then the corresponding stress is called hydrostatic stress. Next, tangential or shearing stress. When a deforming force acts tangentially to the surface of a body, it produces a change in the shape of the body. The tangential force applied per unit area is equal to the tangential stress. Next one is strain. Define the term strain, why it has no units and dimensions, what are different types of strain. Strain. When a deforming force acts on a body, the body undergoes a change in its shape and size. The ratio of the change in any dimension produced in the body to the original dimension is called strain. Strain is equals to change in dimension upon original dimension. As strain is the ratio of two like quantities, it has no units and dimensions. Types of strain. Longitudinal strain, volumetric strain, shear strain. Longitudinal strain, it is defined as the increase in length per unit original length when the body is deformed by external forces. Longitudinal strain is equals to change in the length per original length. Change in length symbolized as this triangle, small triangle, and L, small l, called as delta L upon L. Volumetric strain. It is defined as the change in the volume per unit original volume when the body is deformed by external force. Volumetric strain is equals to change in volume, symbolized as this one, delta V, upon original volume, V. Shear strain. It is defined as the angle theta in radian through which a face originally perpendicular to the fixed face gets turned on applying tangential deforming force. Shear strain is equals to theta equal to tan theta equal to relative displacement between two parallel planes per distance between parallel planes. Elastic limit. What is meant by the term elastic limit? Elastic limit. If a small load is suspended from a wire, its length increases. When the load is removed, the wire regains its original length. But if a sufficiently large force is suspended from the wire, it is found that the wire does not regain its original length after the load is removed. The maximum stress within which the body regains its original size and shape after the removal of deforming force is called elastic limit. If the deforming force exceeds the elastic limit, the body acquires a permanent set of deformation and is said to be overstrained. Next one is Hooke's law and modulus of elasticity. State Hooke's law. How can it be verified experimentally? Hooke's law. From experimental investigation, Robert Hooke, an English physicist, 1635 to 1703 AD, formulated in 1679 a law known after him as Hooke's law, which states that the extension produced in a wire is directly proportional to the load applied. In 1807, Thomas Young pointed out that the strain is proportional to the extension of the wire and the stress is proportional to the load applied. He therefore modified Hooke's law to the more general form as follows. Within the elastic limit, the stress is directly proportional to strain. Thus, within the elastic limit, stress is directly proportional to strain. So, stress is equals to a constant multiplied by strain. Constant due to this. So, stress upon strain is equals to constant. The constant of proportionality is called modulus of elasticity or coefficient of elasticity of the material. Its value depends on the nature of the material of the body and the manner in which it is deformed. Experimental verification of Hooke's law. As shown in figure 9.3, this one, suspend a metallic spring from a rigid support and attach to its lower end a pan and a pointer. Arrange a scale in the vertical position so that a pointer is able to move along it. Read the position of the pointer on the scale when the pan is empty. Place a weight of 50 gram in the pan. Note the position of the pointer on the scale. The difference between the two readings gives the extension produced in the spring by the weight added in the pan. Increase the weight in the pan in steps of 50 gram and note the corresponding extension. Plot a graph between the extension of spring and the total load producing it. The graph is a straight line as shown in this figure. This indicates that extension is directly proportional to load applied. This verifies Hooke's law. So this is extension reading, there is load applied. Like Boyle's law, Hooke's law is one of the earliest quantitative relationships in science. Hooke's law is valid only in the linear position of the stress-strain curve. The law is not valid for large values of strains. Stress is not a vector quantity, since unlike a force, the stress cannot be assigned a specific direction. When a wire suspended from a ceiling is stretched by a weight suspended from its lower end, the ceiling exerts a force on the wire equal and opposite to the weight F. But the tension at any cross section A of the wire is just F and not 2F. Hence the tensile stress, which is equal to the tension per unit area, is equals to F by A. Define modulus of elasticity. Give its units and dimensions. What are different types of moduli of elasticity? Modulus of elasticity. The modulus of elasticity or coefficient of elasticity of a body is defined as the ratio of stress to the corresponding strain within the elastic limit. Modulus of elasticity. A is equals to stress upon strain. The SI unit of modulus of elasticity is Newton per meter square, Nm minus 2, and its dimensions are m, l to the power minus 1, t to the power minus 2. Different types of moduli of elasticity. Corresponding to the three types of strain, we have three important moduli of elasticity. Young's modulus, that is the modulus of elasticity of length. Bulk modulus, represented by this symbol, that is the modulus of elasticity of volume, that is bulk modulus. Modulus of rigidity or shear modulus, represented by this symbol, that is modulus of elasticity of shape. Young modulus of elasticity. Define Young modulus of elasticity, give its units and dimensions. Young modulus of elasticity. Within the elastic limit, the ratio of longitudinal stress to the longitudinal strain is called Young modulus of the material of the wire. As shown in the figure 9.5, suppose a wire of length L and cross-sectional area A suffers an increase in length del L under a force F acting along its length L. Then Young's modulus is given by longitudinal stress upon longitudinal strain. Longitudinal stress is equals to F by area, force applied per area, upon change in length upon original length. Then we have F by A, then it inversed L by del L. So this is the figure, and this del L is the change in length. Area is the area of this circular section, cross section, and force is applied to this direction. In the wire, if the wire has a circular cross section radius r, then y is equals to Young's modulus is equals to F upon pi r square, A area, pi r square into L by del L. If L is equals to 1 meter and A equal to 1 meter square and del L is equal to 1 meter, then Y is equals to F. Thus, Young's modulus of elasticity is equal to the force required to extend a wire of unit length and unit area of cross section by unit amount, that is, the force required to double the length of the wire. Units and dimensions of Y, Young's modulus. The SI unit of Young's modulus is Newton per meter square or Pascal PA, and its CGS unit, centimeter gram second, unit is Dyn per centimeter square. The dimensional formula of Young's modulus is m L to the power minus 1 t to the power minus 2. Next, stress strain curve for a metallic wire we will discuss in the next video. Thank you.